So first, let's start talking about some terminology. There's, first of all, just the idea of a differential equation. Differential equation just means we've got some idea about a relationship between a function and its derivative. Maybe we've got some function y of t, and we don't know what it is. Some unknown function y of t. Some function y of t, we don't know what it is, but we know something about its derivative. Maybe we know that dy dt equals something, usually written as a function of t and y. And that function of t and y could be anything. Maybe we have, for instance, maybe y prime equals y times 5, or y prime equals t squared plus y squared, or even something as simple as like y prime equals 3t to the 5th. And this last one you could actually solve using 21B techniques. If you know y prime equals a function of just t, how would you undo that derivative?
You just integrate it.
In this case, if you just have y prime equals a function of just the independent variable, in this case t or maybe x or whatever, then you can just integrate both sides. So that's essentially a 21B problem. You know the derivative, you're trying to find the original function by integrating. But in these cases, it's more complicated. You can't just integrate both sides of this with respect to t, assuming this is a derivative with respect to t. You can't just integrate both sides of this with respect to t because y itself is a function of t and we don't know which function. If we already knew which function, we'd be done anyway. So just integrating both sides is not enough in cases like this, where you have dy dt equals something about y and possibly t. Solving it is often going to involve some sort of integral, but not necessarily in an obvious way. Also some categorizations here. In this case, we would call this an ordinary differential equation, or usually just abbreviated as ODE. Ordinary in the sense that it only involves ordinary derivatives as opposed to partial derivatives. A partial differential equation would have partial derivatives, and that's typically only going to show up if you've got a function of several variables. For example, let's say y is a function of maybe position and time. If y is a function of position and time, then you could have a partial differential equation involving partial derivatives. Maybe you've got something about partial derivative of y with respect to x and partial derivative of y with respect to t. And maybe you know that they happen to add up to t squared or something like that. So that would be an example of a partial differential equation, PDE. In 22B, we're generally going to focus exclusively on ordinary differential equations. Partial differential equations require some very different techniques. Similar in some ways, but very different in other ways. But that's ordinary differential equation, which has ordinary derivatives, versus partial differential equation, which has partial derivatives. Any questions on those terms so far? And then within the category of ordinary differential equations, there's a lot of subcategories. The thing is, there isn't really one unified way to solve every ordinary differential equation. So we split it up into categories. There are certain techniques that only work on this category, other techniques that only work on this category. Once you know what category it is, you have an idea of what techniques might be useful. So of those, one of the techniques, one of the categories is the idea of order. Order basically just represents the highest derivative that shows up in the equation. Like this, for instance, if it's just first derivative equals something about y and t, that would be a first order equation. First order ordinary differential equation. But if we had something like, let's say, y double prime plus 5y prime plus 3y equals sine of t. This one has a second derivative, so this would be a second order differential equation. In general, order just means the highest derivative of the function we're trying to find that shows up in the equation. In the first couple of chapters, we're going to be looking at only first order equations. Chapter 3 is all about second order equations. And it turns out that the techniques you use for second order equations can generally be extended to third, fourth, whatever order you want. But we're going to start with first order equations and then branch out into second order equations as well. Any questions on those categories so far?
Could you go over why are we doing the categories again?
Largely because there isn't really one universal technique that works for every differential equation. But there are certain techniques that work for everything in a certain category. So for instance, in chapter 3, we're going to be looking into techniques that work for differential equations that look like this. Second order with constant coefficients, just like 1y double prime, 5y prime, 3y. And we're going to be looking into some techniques that work for anything of this format, anything of this category. If it's not in that category, then those techniques won't work. But many differential equations in practical applications fall into certain specific categories. So if you know how to solve that category, then you can solve any differential equation of that type. Any other questions on that so far? And then another big category involved here is linear versus nonlinear. And the exact definition of linear tends to be kind of confusing at first, because linear in this context doesn't mean it forms a straight line. Linear is more in the context of linear combinations that we looked at in 21 or 22A. So what we mean by linear here, if you compare this to linear combinations from 22A, linear algebra, the idea of a linear combination. Let's say you have maybe 3 vectors, v1, v2, v3. What would you do with those to form a linear combination of them? What does it mean to have a linear combination of these vectors?
Is it like adding each of the components of each vector?
We could add them together, but what else could we do with them before we add them and still count as a linear combination?
Multiply them by a constant?
Yeah, multiply by, and it doesn't necessarily have to be a true constant, it just has to be a scalar. So we could have, for instance, a scalar times v1, a scalar times v2, a scalar times v3, and then we add those together. So a linear combination is just the result of taking a collection of vectors, multiplying each one by a scalar, which might be a constant, might not be a constant, might even just be 0, and then adding those together. So this is what is meant by the term linear in higher mathematics. Linear doesn't necessarily mean creates a straight line when you graph it. Linear in this context means all we're doing to the things is multiplying them by scalars and adding them together. And the reason this is called linear is it kind of grows out of the idea of a straight line. That if these are just vectors in, let's say, 3-dimensional space, then the results of this are going to be maybe a straight line or a flat plane through the origin. But the idea of linearity in terms of how we combine variables in algebra doesn't necessarily have to involve graphing as a straight line. It means that all we're doing is multiplying by scalars and adding the results together. If we want to extend this to the idea of differential equations, if we're talking about a linear differential equation, and let's say we're talking about maybe, let's say third order. Third order means we're going to have possibly y itself, possibly y prime, possibly y double prime, and possibly y triple prime. So third order means it could have up to all of these terms. But if we want to say this is linear, a linear differential equation just means we're combining these as a linear combination. Exact same idea as a linear combination from 22A. It's just that instead of multiplying a scalar times various vectors and adding them together, we're multiplying scalars times y and its derivatives and adding them together. The thing is, though, those scalars don't have to be constants. Those scalars could be functions of t. So we could have, the usual terminology is we'd have maybe a0 of t, a1 of t, a2 of t, a3 of t. Add those together. This would be a linear combination of y and its derivatives. And since we want a differential equation, this would have to equal something else, maybe b of t. So this is what a linear differential equation looks like. It's got the function and some of its derivatives, each one of those multiplied by a scalar, which in this context just means a function of t, not a function of y, just a function of t, and then all added up to equal some other function of t. So for example, and of course it doesn't have to be third order. You could have more terms as long as it continues to follow this pattern. For example, you could have something like, maybe you've got a y and a y prime. Maybe y is multiplied by t, y prime is multiplied by negative 3t squared, and that equals cosine of t. This counts as a linear differential equation. Even though t squared and cosine of t are nonlinear functions, that doesn't matter because we're not looking at whether it's linear in terms of t, we're looking at whether it's linear in terms of y. And all this is something times y plus something times y prime equals something. That's our a0, that's our a1, well, the negative would be incorporated, and this is our b of t. So because this is written in this format, or can be written in this format, that means that this is a linear differential equation. And linear is a category that tends to be easier to solve. If a differential equation is linear, there are certain techniques that are guaranteed to work on it, especially first order. We're going to be looking pretty soon at a technique called integrating factors that works on every first order linear differential equation. So if it's first order and linear, there's a technique called integrating factors that will always work. If it's second order and linear, integrating factors won't work, but there are other techniques we can apply. Any questions on that so far?
Would that have an effect, or would having let's say like cosine t of y on like the b of t side, would that have like effect on the linearity, or?
Like if it was cosine of ty?
Yeah, something like
Yeah, this would
that.
immediately make it nonlinear.
Okay.
Because the important thing is that nothing nonlinear is being done to y itself. You can have all sorts of weird functions applied to t or x or whatever the independent variable is. But as soon as you have a nonlinear function applied to the function you're trying to find, in this case y, that immediately makes the differential equation nonlinear.
Okay.
So for instance, another nonlinear example might be something like, maybe you've got like 3 square root of y plus y prime equals 5t. The fact that you've got this square root of y is going to make that nonlinear. Or if you've got some sort of combination of maybe y and y prime being multiplied, if you have something like, even something as simple as y times y prime equals 1. This counts as nonlinear because there's no way you can write it in this format. This is not a linear combination of y and y prime. Instead, it's y and y prime being multiplied. So anytime you've got y or one of its derivatives being multiplied by each other, or y or one of its derivatives raised to a power other than 1, or square roots of y, or cosine or sine, any trigonometric functions of y or its derivatives, that would make it nonlinear because there's no way to write it in this format. Any questions on that so far? And one other important subcategory of linear differential equations, assuming you've got a linear differential equation if b of t happens to be 0, then we call the equation homogeneous. And as you might expect, it is a lot easier to solve if b of t happens to be 0. And of course, that doesn't have to mean it looks like equals 0 on one side. These could be arranged in any way. You might have some of these terms on the other side. The important thing about b of t is it's the term that doesn't have y in it. So for instance, if we write an equation like, let's say, 5y equals 3y prime plus y double prime, this counts as homogeneous, even though it doesn't look like equals 0. The important thing is there is no term without a y in it. Every term has a y or a y prime or a y double prime or whatever. And you can easily write this in the correct format, or the useful format, I guess I should say, by just, let's say, subtracting 5y from both sides. This, I think, makes it a lot more clear that this is homogeneous. If you move all of the terms with y to one side, and any terms without y, if there are any, to the other side. So this would be an example of a homogeneous second order linear differential equation. And moreover, we'd say with constant coefficients. The fact that all the coefficients are constants rather than functions of t makes it even easier to solve. In fact, chapter 3 is all about differential equations like this. Second order, linear, constant coefficients, and to begin with, homogeneous. We'll look into non-homogeneous equations towards the end of chapter 3. Any other questions on the terminology there so far? One other important thing about homogeneous equations, if you just have a bunch of stuff about y adding up to 0, what's one value you could plug in for y that will always work there? Yeah, 0 will always work, right? If you set y equal to 0, then of course the derivative is 0 and the second derivative is also 0. So if you plug in 0 for y, that makes this equation true, which means 0 is a solution to this differential equation. In fact, this is a perfectly valid alternative way of defining homogeneous. You could say homogeneous means 0 is a solution. Whereas for a non-homogeneous differential equation, 0 will not be a solution. And by solution, what do we mean by a solution to a differential equation? If I claim some function is a solution to a differential equation, how would you check that it's really a solution?
Would like fit the conditions of the differential equation?
Yeah, we want to check, does it really fit those conditions? And yeah, that will definitely involve taking the derivative. Because a differential equation is really just a description of how the function and its derivatives are related to each other. So if you want to check, is this function a solution? You just check, does that function and its derivatives make the equation true? So if you have a function and you want to check, is this really a solution? You take as many derivatives as are needed, whatever the order of the equation is, plug in the function and its derivatives and check, does that make the equation true when you work it out? If yes, then yes, that's a solution. If not, then it's not a solution. Any questions on that so far? Also, while we're on the subject of solutions, if you just have some differential equation, and let's start with probably the most straightforward differential equation that's not just a 21B problem. Let's say we have dy dt equals, let's say, -3y. So the only thing going on here is we have some unknown function, and all we know about it is that its derivative is proportional to the function itself, specifically -3 times the function itself. And we can't solve this by just integrating right away because we can't integrate y with respect to t. But what could we do here to rearrange things so we can integrate? Is there any way we could move variables around here?
Could you divide y by both sides?
Yeah, if we start by dividing both sides by y, that at least gets rid of the y on this side. Then we'll have 1 over y dy dt equals -3. Problem is we still have a mixture of y and t on this side. Is there any way we could get rid of that dt?
You multiply it on both sides.
Yeah, if we multiply both sides by dt, and this is kind of cheating because dt is not technically a separate thing. This does not mean something called dy divided by something called dt. It means the derivative. But multiplying both sides by dt is really just a shortcut for longer method using the chain rule and use substitution. Formally, we're taking the integral of both sides with respect to t. The dt's cancel out, we get an integral with respect to y. But you can also write that as, if you imagine just multiplying both sides by this imaginary thing called dt, you could imagine the dt's canceling out, so you get 1 over y dy equals -3 dt. And then integrate both sides. This is what we call separating variables. What we've done here is we've split up the variables so we have just y on one side and just t on the other side, and possibly some constants on both sides. But once we've separated the variables, now we can actually integrate. Apply an integral sign to both sides. And what's the integral of 1 over y with respect to y? Yeah, we get natural logarithm of y. And on the other side, what's the integral of -3 with respect to t? Yeah, -3t. Also, we're not really looking for just one solution. Ideally, we want to find all possible solutions. So what else should we include here?
A constant?
Yeah, we should include that constant of integration, just plus some constant, usually c. Because we're really looking for all functions that make this differential equation true, all functions that have this fact about the slope. In fact, this is very similar to, I mean, since a differential equation is just describing something about the slope, this is very similar to knowing the slope of a line, but not knowing what the line is. Like if I said, I want you to graph a line with slope 3, how many possible lines are there with slope 3? Yeah, infinitely many, right? You could have this one, this one, this one, this one, this one. There's infinitely many parallel lines that all have slope 3. So this is very similar here. We're looking for all functions that have this fact true about the derivative. And it turns out there's infinitely many functions because this plus c could have been anything. And for that case of the line, if I just tell you graph a line with slope 3, there's infinitely many such lines. What other information would you need to narrow it down to just one line? You need the slope and also what other information? Yeah, you need some point, some initial condition. For a line, you just need a point that it goes through as well as the slope. And the same is true for differential equations. The differential equation allows you to create a family of solutions, a collection of all possible solutions with some unknown constant in it. If you also have an initial condition, a point that the graph goes through, you can narrow that down to one specific solution. So let's say we also know that, let's say, y of 0 equals 5. These two pieces of information together, the differential equation and the initial value, is called an initial value problem. Usually abbreviated as IVP. So IVP is an abbreviation you're going to see a lot, as well as ODE. So ODE, ordinary differential equation, just anything with ordinary derivatives only. IVP, initial value problem, consisting of the differential equation and one point that it goes through, one point that the solution goes through. With that information, you can solve for C and figure out the specific solution. One other thing we should probably do here, though, ideally, we just want y equals some function of t. So what else do you need to do here to isolate y?
to e to the power of both sides.
Yeah, we can use the exponential function. E to the power of the left side equals e to the power of the right side. On the left side, what happens when you raise e to the power of logarithm of something?
It's just the thing in the logarithm.
Yeah, the exponential and logarithm functions cancel out, so we're left with just the inside of the logarithm, y itself. Y equals, and then on the right side, there's something else we can do. If you've got e to the power of something plus something, how can you split that up?
Multiply it, like the c times e to the minus 3.
Right, we can split that up as multiplication. Addition inside the exponent becomes multiplication outside the exponent. E to the negative 3t plus c becomes e to the negative 3t times e to the c. But what does c represent in the first place? Do we know what c is yet?
It's just a constant.
Yeah, c is just some arbitrary constant whose value we don't know yet. And if c is just some arbitrary constant we don't know yet, then e to the c is also some arbitrary constant whose value we don't know yet. So we can replace e to the c with another constant, let's say just capital C. And there's our general solution. So this represents the infinitely large family of solutions that make the original differential equation true. And you can always check that by plugging it in. Take your function and its derivative, plug those both in, and you should find that the derivative is exactly negative 3 times the original function. In fact, let's take a moment to check that now. We are saying that y is c times e to the negative 3t. If we try taking the derivative, what would be the first derivative of this with respect to t?
Would it be minus 3c e to the t?
Yeah. The constant multiplier stays where it is. Exponential function is still exponential function when you take the derivative, but due to the chain rule, we need to multiply by the derivative of what's inside, which is negative 3. And notice that what we have here is y itself times negative 3. So we've just proven that derivative of y equals negative 3 times y itself, which is exactly what the original differential equation wants. So this is a solution to, in fact, this is all solutions to the original differential equation because it's all the functions that make it true. Any questions on that so far?
Yeah, so when you have the initial value, so do you find the, do you use the, do you find the general solution and then you apply the initial condition?
Right, find the
generally
general
how it works?
solution first. And then once you've got the complete general solution, then plug in the initial condition. So we would say here that the general solution is c to the negative 3t. And now we can plug in the initial condition to get more information about it. So plugging in the initial condition, we can say, we know that when t is 0, y is 5. And the initial conditions are usually at t equals 0. They don't have to be, but the math is a lot easier to work out if it happens to be at t equals 0. Because when we actually plug that in, when we replace y with 5 and replace t with 0, we just get e to the 0. What's e to the 0? So we just get c times 1. In other words, 5 equals c. And more generally, in a case like this, if you just got y equals c times e to the whatever, then the c value is just going to be the y value at time 0. So we would say the specific solution that matches these initial values is y equals 5 e to the negative 3t. So the general solution is listing the family of all infinitely many functions that make the original differential equation true. The specific solution is picking out the one of those that matches the initial conditions as well. And again, you can think of this as very analogous to knowing the slope of the line and knowing one point that the line goes through. Because the derivative is effectively telling you about the slope, it's just that the slope is changing rather than a constant. Any other questions on that so far? Also, let's go ahead and categorize this. Based on the category names we were looking at earlier, how would you categorize this differential equation? What do you know about it?
It would be a first order ordinary differential equation.
Yeah, this is definitely first order ordinary differential equation. Ordinary because it only includes ordinary derivatives. There's no partial derivatives. Definitely first order because there's only a first derivative. Is it homogeneous? Good question. How do we check if it's homogeneous or not? Yeah, if it's, well, not necessarily if it's equals 0 in the equation format, but if 0 is a solution. Because the alternative definition of homogeneous is, does 0 make the equation true? So is y equals 0 a solution? So if we check, if we replace y with 0, and then of course y prime will also be 0. You plug in 0 for y and 0 for y prime, does that make it true? Does 0 equal -3 times 0? Yeah, 0 is a solution. So that suggests, yes, this is homogeneous. It might not immediately look homogeneous because we don't have equals 0 in the equation. But of course, you could rearrange it. If you just add 3y to both sides, you get y prime plus 3y equals 0. So if we put it in the standardized format, something y prime plus something y equals something, the something on the other side ends up being 0. And that's ultimately because this does not contain any terms without y. Every term has y or one of its derivatives in it. The non-homogeneity, the b of t term, is the term without any y in it. If every term has y in it, there is no non-homogeneity. So this is a homogeneous differential equation. So it's first order, it's homogeneous. Does it count as linear?
Yes.
Yeah, definitely linear. There's nothing nonlinear being done to y. And moreover, its coefficients are all constants. We've got 1 y prime, we've got -3y. This has constant coefficients. So I guess we could generalize this to, if we just have, let's say, y prime plus, let's say, a times y, where a is just some constant, then we should expect that's always going to lead to the same type of solution. Because this didn't have to be -3, this could have been anything. If y prime plus ay equals 0, our solution should be something times e to the -at. Because when you plug that in, the derivative becomes -a times ce to the -at. The -a times y and the +a times y cancel out, you get 0. So this general solution works for any differential equation of this format. Anytime you got y prime plus ay equals 0, or to put it another way, y prime equals -ay, the solution is always going to look like this. So this is where the whole idea of exponential decay comes from. If the rate of change is proportional to the function itself, that always leads to exponential functions. And this shows up in all sorts of applications. If you're talking about, like, for instance, what's a situation where you would expect the rate of change to be proportional to how much there already is? What sorts of real world scenarios often involve exponential growth or decay?
Like population.
Yeah, population growth. Population growth, assuming there's no limitations like limited resources or limited amount of space available, population growth tends to follow exponential patterns because in population growth, the rate of change is proportional to how much population there already is. The more individuals there are, presumably the higher the birth rate is going to be. So population growth tends to follow exponential patterns because the growth rate is proportional to how much there is right now. And that inevitably leads to exponential functions. What are some other examples of exponential growth or decay in the real world? Yeah, spread of diseases. If you've got a disease in a population, the more individuals have the disease already, the faster it's going to spread. So once again, how fast the disease spreads is proportional to how many people already have the disease. And it gets a little more complicated if, well, a lot more complicated really, if a significantly large portion of the population has the disease. Because then you've also got to model things like how many uninfected people are coming into contact with the infected people, how many people have already had the disease, whether or not that makes them less or more susceptible to getting it again. So disease modeling gets really complicated really fast. But you can make a very simple model, a simple approximation of it using this same population description, population growth model. And yeah, population of bacteria, any sort of population where the more there is right now, the faster it grows or spreads. Also things like radioactive decay. If you've got a sample of some radioactive element, maybe uranium or something, then it's going to decay. But at any given span of time, like let's say every 100 years or something, every atom has a certain percentage chance, a certain probability of decaying to a different kind of atom. So that also tends to follow this sort of model, because the more atoms there are right now, the faster they decay in terms of number of atoms per year or whatever. So the more of it there is right now, the faster it's going to decay. That also leads to exponential patterns. Any situation where how much there is right now directly proportionally determines how fast it's changing, that always leads to exponential decay. And in fact, more broadly, even for non-first order, for higher order, second order, third order, and beyond, as long as it's linear, homogeneous, and has constant coefficients, exponential functions are a good starting point. If you're not, in many cases, if you're not sure how to solve a differential equation, one frequently useful approach is to make a guess. Make a guess, and then how do you check if the guess is really true? How do you check if something's really a solution or not?
You plug in the solved y into the original differential equation and see if it's true.
Plug in that function and all its derivatives into the original differential equation and check if it makes the equation true. So you can often get a lot of useful results by making a reasonable guess. And as long as it's linear, homogeneous, and constant coefficients, an exponential function is going to be a good guess. So maybe you guess e to the something t, where that something is an unknown constant, plug it into the original differential equation, and that tells you a couple of useful things. First of all, it gives you an idea of whether that function is even going to work as a solution. And second, it gives you a new equation that you can maybe solve for that unknown coefficient. So even if we hadn't known about this separation of variables idea, if we have the general idea that this should lead to an exponential function, you can guess that y equals e to the something, let's say e to the rt, take its derivative, plug those in, and then you get an equation you can solve for r. So this is often a very useful approach to many differential equations. Make a reasonable guess of a type of function you think is going to work with some unknown parameters in the equation. Plug in that function with unknown parameters, and that gives you an equation you can solve for those parameters. So that's often a very useful approach, especially for higher order equations. Any other questions on that so far?
And how can we make a reasonable guess?
A reasonable guess?
Mhm.
First of all, anytime you've got a linear differential equation with constant coefficients, e to the something t is always going to be a reasonable guess. And we're going to look into that in more detail in chapter 3 when we look at second order linear equations with constant coefficients. If e to the whatever t doesn't work, then take a look at some of the other terms and try guessing solutions that look like those. Like if there's a lot of t to a whole number power, maybe guess t to the n as a solution and see if that works. And then you'd be solving for n. Alternatively, if you have some advanced knowledge of what the situation's behavior looks like if you observe a physical phenomenon and you notice that it's oscillating, what's a function that you already know that oscillates?
Sine or cosine?
Right. So if you already know that you're dealing with a physical situation that exhibits oscillatory behavior, and you created a differential equation to model it, maybe try guessing sine or cosine with some unknown parameters, maybe like sine of AT plus cosine of BT, some unknown coefficients in the sine and cosine functions. But typically you can often get a reasonable guess either by looking at the equation and comparing it to functions and derivatives you already know, or by examining the physical real world behavior of the system and ask yourself, what functions do I already know that look like this sort of behavior? Alternatively, even if it's not a physical real world system you can observe, you can often get an idea of what the behavior looks like using this idea of a direction field. The whole idea of a differential equation is that it describes the derivative, the slope at every point. If you have, anytime you've got dy dt equals something about t and y, if you have a point on the graph, a t value and a y value, you can plug those in and find the slope at that point. So the whole idea of a first order differential equation is it tells you the slope at every point on the graph. We can also show that visually by drawing a direction field. The direction field shows you the slope at every point on the graph. For example, if we try drawing out a direction field for this equation, we could just start plugging in some numbers. Like let's say you take the origin, 0, 0. You plug in 0 for t, 0 for y, what do you get here?
You get 0.
Right, which means that at the location 0, 0, the slope is going to be 0. So I'm going to draw a little line segment or arrow or something with slope 0. Or what if we go up to 1? You plug in 1 for y and let's say 0 for t. And what do you get for the derivative? If you plug in this point, 0, 1. Plug in 0 for t, 1 for y, and what do you get here?
-3.
Right, so that means at this point, the slope is -3. Or what if we plug in 0, 2? What do we get for the slope?
-6.
-6. So it's going to be even steeper downwards. And it'll just get steeper and steeper the higher we go. Or what if we plug in -1 for y?
Uh, 3.
Right, we get +3 as the slope. Or you plug in -2 for y and you get
6.
So at this point, the slope would be 6, much steeper positive slope. And we could plug in more points as well. In this case, though, what happens if we go one space to the right? If we keep the same y value but change the t value? Like, let's say instead of plugging in the point 0, 0, we plug in the point 1, 0, or 2, 0, or 3, 0. What happens to the results of the differential equation?
It doesn't change because there's no dependence on t.
Exactly. This does not depend on t at all. And so we actually have another category for that. This is called autonomous. This differential equation is called autonomous because it is time independent. We have y prime equals a function of just y. If the differential equation is derivative equals something about just y, no t at all, this is called an autonomous differential equation. And that makes the direction field much easier to draw, because if we take this column we've just made and just move one space to the right, one space to the right, one space to the right, we're not changing y, so we're not changing the results. So if we take this column and just shift it, it'll be exactly the same. We'll have slopes 0, -3, -6, +3, +6. Then we can just take this column and copy, paste, 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 paste. And because the differential equation is autonomous, it's just going to be more copies of the same column. So this would be at least a piece of the direction field. And you could, of course, put in more detail. You could plug in more data points, maybe halfway between these or something. Use the differential equation itself to calculate the slope at that point and draw it in. And drawing out the direction field can be kind of tedious because you've got to plot so many points. So it's often very useful to use a computer program to graph the direction field instead, to get a look at what the direction field looks like in a hurry. But once you've got the direction field, you can draw in sample solution curves as long as you've got some initial value. Like let's say we use the initial value 2. The graph says at that point, the slope is steep downwards. But as we go downwards, we get to a region where the derivative is less steep. And then it gets less steep and less steep and less steep. So it's going to look something like this. Or if we start here, we've got a steep downward slope. As we go further down, it gets less steep and less steep. Or if we start down here, we've got a steep positive slope. But then we get to a less steep region and less steep. So we're going to get solutions that look like this, paralleling the direction field arrows as much as possible. Also, what happens if you start at 0? If your starting y value is 0, what's the slope going to be?
0.
Right, which means you just stay at 0. So this would be called an equilibrium solution. An equilibrium solution is a value where if you start at that value as the initial value, you just stay at that value forever. And then typically all of the other solutions nearby are going to use that as an asymptote, either approaching the asymptote or diverging away from the asymptote. But in this case, just based on the direction field, even if we hadn't solved this analytically, even if we hadn't known about using separation of variables, we can see from the graph that all of these solution curves look like what sort of function?
Exponential functions.
Yeah, this looks very much like exponential decay from both sides. So that means even if we didn't already know it, the direction field would suggest, oh, maybe we should try guessing e to the something t and see if that works. So the direction field can also often give you a useful idea of what the solutions look like, especially their behavior. Are the solutions converging towards some asymptote or diverging away from some asymptote or oscillating or what? And that often gets you the information you need to know about the situation, even if the original differential equation can't be solved analytically. So a direction field is a very useful tool for predicting the behavior of a system, even if you can't solve it with regular calculus techniques.